Hello again. Time for another revision short video. Hair getting longer. Nothing we can do about that. I was asked about flame tests, but that leads into the two types of spectra that are intrinsically linked to them. Yes, you do have to remember flame colours. Here they are for the ones that you have to remember. Group 1 and Group 2. If you look in the bigger wide world of chemistry, there are endless numbers of flame colours associated with other elements. Sometimes there's conflict about what it is and it just seems to go on forever. So they restrict it pretty much to Group 1 and Group 2. Some exam boards do include copper and lead. Copper is a sort of bluey green and lead is a sort of greyish white. You have to check with your exam board which ones you need to know, but they all have these ones common to them. You may have done them, you may not have done them. I know the school I work in doesn't have a suitable rubidium or cesium salt, so it's a case of that's what you have to learn. Now, one of the things about this is I'm not a big fan, and a lot of people are not big fans actually, of what I think of as modified colours. So when someone says red, they go, actually I meant crimson, that's a modified colour. Like here, apple green, I prefer green. I mean, I'm not very good at seeing colours anyway, so it's all a bit lost on me. But green is fine. You may have been told apple green. So everyone at Group 1 has a notable colour. There was a little bit of conflict about what shade of the red, violet, blue ends of spectra you get for rubidium and cesium. Lithium, distinctly red. Sodium, really obviously yellow-orange, to the point where a small contamination of sodium into a sample, it's just going to look like sodium regardless. Potassium is the only one with an odd colour description, lilac. But that's the one that you see all the time, you see it as lilac. Now potassium is particularly well, spoiled by the presence of sodium. When you extract sodium from the natural environment, it comes out mostly salts from the ocean in one form or another that have either been deposited in the past or you can get them out of the ocean. The same is true for potassium, so they tend to be found together. So getting all of the sodium out of a potassium salt, really difficult because they're both Group 1. So you often see potassium being spoiled by the presence of sodium. And your fingers are covered in sodium as well, so, well, sodium ions I should say, not sodium metal. And as a result, touching things does tend to contaminate them with sodium. Group 2, the top two, no flame colour. I mean, technically they do have a flame colour, it's just that your eyes are not capable of detecting it. Because beryllium and magnesium are 2+ ions, and therefore the electrons, which will do what happens, but the electrons are pulled down really big energies. That energy is ultraviolet and it's outside the visible. Calcium, a much larger ion. When ions are larger, you tend to see things at the lower energy end, which is the red end, or even in the infrared, to be honest. And so strontium is red. Barium, on the other hand, seems to be green. But it's not very, I struggle to it when I do practicals with people to see the green in barium. It seems quite subtle. It's quite hard to detect because it is a pale green. And I said two others, copper and lead. Now people go to me, how do I remember them? Well, the answer is learn. You've got two choices. You can learn them, or I came up with this recently. It's not terribly helpful, but Roy, little red boy. So going from the top, lithium, orange yellow for sodium, Lil for lilac, red for rubidium, and B for blue for cesium. It's like that whole thing with this, you know, the 7 colours of the spectrum and all the stuff to do with that. When you look at group 2, obviously that's different, and I came up with no brag. It's not quite so good, but it's all I could come up with. So none, brick red, because this is the colour that you often have to write as the answer, and then red for strontium, and then apple green for barium. So little red boy, no brag. Up to you. Now, what we're going to do is we're going to explain the origin of these, but I need to get the board clean, so we're going to have a little break. See you on just on the other side of the edit. So you need to know that there are 2 ways to do flame tests in the laboratory. A lot of people do the piece of metal wire, nichrome wire is usually used. Now nichrome wire does tend to give a yellow flame colour on its own because of the elements in it. You want a true piece of wire that does it, you have a piece of platinum. Cost wise, not going to happen in schools. And you take that piece of wire, you dip it in concentrated hydrochloric acid, you put it in the flame, you do it until it's not really colouring the flame very much. Then you dip it in the salt, it needs to be a bit wet with the hydrochloric. You need to keep changing the hydrochloric as well because it gets contaminated. And you pick up the salt, put it in a blue Bunsen flame, which is called a non-luminous flame, and it does the magical colour that you ever see. And more recently, a method has been a wooden splint soaked in a reasonably strong solution of the salt that you're trying to test, and you put that in the flame. Because it's soaking wet, it doesn't catch fire with the yellow flame, and the ions stream up into the blue Bunsen flame. Although the tendency is to leave it there for too long and it dries out and catches fire, which is not what you're trying to do, because that is not the flame colour you're looking for. But that's quite successful. And either of those 2 methods are the ways to do it. Sometimes they're more successful than others. One of the things that lets you down is the purity of the salt that you're testing. Chemicals come in a number of levels of purity, and in order to get a proper flame test you need a grade of reagent that is quite expensive, which is why some schools don't have the rubidium and the cesium that I mentioned earlier, because they are quite expensive. Yeah, so you get a flame colour. Take sodium as an example. Sodium yellow orange. Is that it? No. One of the things you need to be aware of is that any element, sodium as an example, is not just one colour. It has a number of lines. Now there's a thing called a slit spectroscope, which is the ones I use are metal tubes, and they have a little narrow slit at one end, and you look down the eyepiece with a little lens, and you see, when you look at that, lines of colour. If you go to get it in the right angle, you have to not, to be honest, you have to not set your hair on fire, because you get quite close. And you look down this through the eyepiece and you see there are lines of colour. When you look at the sodium as an example, it's a really bright yellowy orange line. In fact, it's 2 lines right next to each other, which is why it's bright. And that tends to dominate the colour mix that your eyes perceive. So your flame colour is determined by your eyes mixing together the information of all the various colours of light it is receiving. But of course that mix is dominated by the brightest line, and that tends to be associated with the colour that you see. So when you look at strontium, the red lines are quite bright. There are lots of them, so you get a shade of red. Now, that's slit spectroscope. I find difficult to explain to people how to use. I can use it, but getting it across to people, quite difficult. But when you look at it, you do see distinct lines of colour and just nothing in the gaps. Now there's a reason behind that, and that is the reason that you have to be able to put out in a explain the origin of flame colours question. Now, staircase is similar in some respects to what you do. There's a thing called ground state. Now when you look at electronic structures, 1s2, 2s2, 2p6 and all that stuff, kind of stuff. That's called the ground state, and that's the energy levels filled up from the bottom in order. Put that ion, which will have an electronic structure, in, well, anywhere hot. Well, we use a Bunsen flame in a school laboratory. Bunsen flame 800, fairly hot. Electrons get thermally excited, so they go upstairs. So they would start their life down here, and maybe they'll be in the ground state. There'll be two there as well, and they will get all that thermal energy, and they will go up. And there might be some there and some there. So they will go from there, and they'll go up there, and then as they get to the outside of the flame, they cool down. And what happens is they come back down the stairs. Now this is a false diagram. So for them to come down the stairs, what they could do is that. That will produce one line, two lines, three lines, four lines. It's a false diagram because the steps are the wrong size. A little bit of magic, because the magic is more like this. Now the staircase is uneven. So that electron that came down with 4 steps, with 4 releases, would be 4 lines visible in the, what it's called an emission spectra. We'll do emission and absorption spectra near the end. But it would give you 4 lines. They would not all be the same. Now, the size of the jump reflects in the size of the energy that comes out as the electron loses it. So this one here is a small jump. This one's likely to be at the red end of the spectrum. This one's a much bigger jump, so it's much more likely to be blue. There's a slight false because you don't actually come back up again before you go down. You literally just go off and fall off the step. But I've done it as a bouncing thing. So you'll get red and blue there, and these will be in the middle, maybe green or something like that. So there is an electron, and it's hitting every step. Not the only choice. Could do, with this one say, it could go to this one here. So that would then drop down that distance, and it would miss out some of the steps. You do not have to come cascading down, hitting every energy level on the way down. You can miss out 2, 3, 4, 5 and do big jumps down, because there are lots of energy levels. So you get single step jumps, you get 2-step, 3-step, 4-step, multi-step jumps where it misses them out. The bigger the jump, the bluer the line. So you get lots of red lines because there were lots of small jumps, and not so many of the bluer line. So bluer flame colours are not so common. Now that results in the emission of a photon. That photon, we've been joined by a fly, the photon is, well, reflecting the size of the energy jump. It is one of the pieces of evidence for electrons being in energy levels within atoms and ions. Don't get flame colours for negative ions, you only get them for positive ions. I have no idea why. I'm sure you do. If you investigate it, you have some kind of answer to that somewhere. But we only ever do the flame colours of positive ions, and they're limited to group 1 and group 2. So it's this coming down the staircase, except there's another falseness in here, because really this diagram should not be like a staircase. They should be stacked up over the top of each other as a set of lines that just comes down. But I think a staircase is a little more visible. Now we're going to have a little cut whilst I get prepped for the remaining bit. See you in a moment. Alright, last little bit then. Emission spectra and absorption spectra. Got to get this done quickly. Got to get a cup of tea and some cake down. So, emission spectra are the, well, they're the flame colour version. Flame colours are where the electrons have gained the energy, they lose the energy, ka-chung, 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 and the energy comes out. So when you look at an emission spectra, most of it is blank. And this, if this line represents red to blue on the visible, what your eyes can see, Some flame colours, like I said, magnesium and beryllium are the two examples you need to know. All their lines are out here, past the blue end or past the violet end, so they're ultraviolet. Now, when you look at an emission spectrum, get your Latin right, there will be a few lines. There tend to be a few more lines down the red end, so there will be some lines. Some of those lines will be brighter than others, and then colour mix will be dominated by the brightest one, and it will influence the mixture that your eyes detect, and that will be the flame colour you see. Analyse the spectrum with an actual mechanical device, you will see a series of lines. Do that more carefully, you can measure the amount of substance that you are detecting in terms of how bright each line is. Now, so you will see mostly blank and some lines of different colours. So here we would have some red lines, there might be an orange one there, a green, and down here for a blue. So you will get a few lines and a lot of black, or if you've got a white background, white, but usually a black background, it's easy to see. Absorption spectrum just turn the whole process upside down. In an absorption spectra, what you do is you have red to blue, so you have the energy going in a direction, and you put elements in the way. So what then happens is, if you did this same element as an absorption spectrum, I doubt the lines match up, I'm too close to the board, but what you would get is red, orange, yellow, green, blue as light, but there will be black lines. And the black lines are where electrons have taken in a particular frequency of energy and jumped up. So it literally is the reverse of the flame colour and emission spectra. Emission spectra have the same explanation as flame colours. That is, excite the electrons, let them come back down again. Absorption spectra start at the ground state, put the energy in and let the electrons jump up. More useful to astronomers probably than anyone else, because it allows you to detect the elements in the outer parts of stars. So the energy comes out of the star and frequencies are missing because of elements. And you can then go, oh, that star's got, and you can measure how much as well, but that star's got iron and that star's got magnesium or carbon or whatever you're looking at. It's bound to have hydrogen, a whole load of lines for hydrogen. So they are literally the negative of each other. Here, bright lines on a black background. Here, black lines on a coloured background, with the lines in exactly the same place, except that stars are moving. I'll leave you with that thought. Shift. There are some questions that I have written to go with this bit of revision, and they do have the answers with them, so you can test yourself and, well, you know, adjust your learning. Thank you for watching, and I'll see you for the next revision video that will be coming up shortly. Bye bye.